we have static equilibrium. Okay, let's take an example. You got a seesaw. Well, you know what? Not a seesaw. I was driving today by Mass Mutual, and I noticed the guy's going to be cleaning the windows. I don't know why it was raining, but this is what I saw. I saw a platform like a piece of wood, a rope attached to it this way, a rope attached to it that way. Assume this piece of wood is uniform, so it has a weight in the middle of it. Let's give it a mass, that beam itself, the piece of wood. I'm sure it's a decent size, heavy piece of wood. They're not going to use a cheap one if you're standing on 20-story high. I'm sure it's steel even, it's not even wood. But we'll use the mass of 100 kilogram. It's not a cheap, like a plywood that will break and people will fall. You got a person standing here. Let's give you the length of that. We'll say that beam is what? Maybe 2 meters, about 8 feet. A bit less than 8 feet, 2 meters long. You got one person here cleaning, standing there. And this person has a mass. Mass of the person, we'll say 70 kilogram. And let's say he's standing from, I don't know, 0.5 meters from the edge of this cable. You get the bucket of the water that has the water in it here. This is the bucket. And the mass of the water here is 20 kilogram. And that water is actually, let's say it's also 0.5 from this end. And I was noticing the thing wasn't spinning. What will happen if this person walks to the edge where the rope is, stood right there at the edge of the rope? What do you think will happen? It might spin in that direction. So this is really free to spin. That beam is free to spin if you're not careful. If you tie them out here and you step, see that little piece sticking out here? And if you go beyond that point, you step on it, guarantee you that thing will spin. So this is actually free to spin. The reason it's not spinning because we have equilibrium. It's called static equilibrium, balanced system. And when your system is balanced, there's 3 reasons why it's balanced. The net force in the x direction is 0, because if you have force in the x direction, it's going to move left to right. The net force in the y direction is also 0. If there's a net force in the y direction, it will move up and down. And the last one, the net torque is also 0. That's why it's not spinning, that beam. It didn't go, whoop, flip this way and you go flying. Now, these cables, guarantee you the tension in them will not be the same. You got a heavy person on this end, there's more tension on this cable. So I'm going to label the tension on the cable T1 and T2. The cable is pulling up by T1. This cable is pulling up by T2. So let's do a free body diagram, show the beam. Here's the beam. Let's begin with the weight. The weight of the beam itself is the mass of the beam, which is what? 100 times gravity, which is 9.8, which is what? 980 Newton. You get the cable here, T1 pulling up. You get T2 pulling up. You get the weight of the bucket. Or the water, I use it. W, the weight of the water, which is the mass, 20 times 9.8. That's 196 Newton. and that's 0.5 meters from this edge. This is 1 meter from the center. The weight, since that's a uniform beam, the weight's going to be halfway between. So it's a 1, if you mark this as the 0 meter, that's the 1 meter, that's the 1.5, because it's 0.5 from here, which means 1.5 from this end, if that's your 0 mark. If this is your 0 mark, this is 0.5, that's 1. Then you get the weight of the person right here. Which is 70 times 9.8. And that's 686. And this is 0.5 meters from the edge from here.
Should the other one be 0.5 or should it be 1.5?
Well, I'm measuring the distance from here.
Okay.
So that's a 2 from this end, right?
Oh, okay.
So if I use this as a pivot point, I can use any point as a pivot point. I chose that one for no reason. And the thing is not moving. Let's see if we can calculate T1 and T2. How much tension on these cables? Sum of the forces in the x direction is 0, which means all the forces pointing to the right should equal all the forces pointing to the left. What do we have pointing to the right and left? Nothing in this example. I'll give you one where you have force left and right, but not here. In the y direction, sum of the force in the y direction, the net force is 0, which means up equals down. What is pointing upward? T1 plus what? T2. What are the forces down? 196, 980, 686. (1862 Newton). So notice there is one equation by how many unknowns? 2. I need another equation with 1 or 2 unknowns in it. So I use this one, I use this one. What's left? The torque. Let me do the torque. And again, you can pick any point for the torque. Any point on that beam, if nothing is spinning, and the sum of the torque has to be 0. I'm going to pick that pivot point just to make my life easy, because I have all the distance already measured from it. If I pick this point, I got to go back and recalculate every single distance. So why? So I'll pick that point. Sum of the torque is equal to 0. Well, you have to visualize now, there's a pivot. There's like a little nail going through that into the wall, and this one's free to spin around that. T1 has 0 torque. Why? What is the distance between T1 and the pivot point? 0. Any force that goes through that pivot point has a 0 torque. So it's going to be T1 times 0. Don't worry about it. It's not going to do anything. It's gone 0. Let's look at the 0.5. I mean this one, not the 0.5, the mass of the person, that weight, the 686. Just that force, if that's the only force acting on that beam, is it going to make the beam spin clockwise or counterclockwise? Let's try again. Just this weight pulling down. This is a pivot point, right? So the beam is going to come down, right, Jason? So it's going to make it what? Counterclockwise. That's a negative. Oh, positive, right? We use positive for counter. Well, it doesn't matter, but our book uses positive for counter. That's what? 686 times the distance, which is 0.5. Let's look at the beam itself. Has a weight of 980. is going to make it spin which way, clockwise or counterclockwise? Just the weight pulling down. Neglect all the other forces, just the weight of that beam. Clockwise. Distance is 1. Look at the bucket of the water, which is the 196, the weight. That's also counterclockwise. And the distance from here to the pivot point is what? 1.5. And what about that tension, the cable pulling up on it? What's the cable going to do? Again, I don't see these forces. Neglect all of these. You don't see them. All you see, you got a beam, and you got somebody pulling up on it. It's attached to a pivot point here. There's a hinge on it here, and you're pulling up on this direction. It's going to make it go up there clockwise. That's a negative torque. And the value of that is the force, which is T2, times the distance from here to there, which is what? 2. All of that should be 0. So how many unknowns do you see there? Only 1. This is gone. $686 times a half, that's what, 343? Plus 980 plus 294 minus 2T2 is equal to 0. Move this one to this side. $1,617, what's T2 is equal to? Divide that by 2. 808.5 or 80, yep, which is 810 Newton, 2 significant digits. Can we find what T1 is? From this equation, T1 plus T2 equals 1860. We know T2 is 810. Oh. So T2 is 810, not T1. T2 is 810. Can we get what T1 is? 1860 minus 810, 1050, and if you're looking for 2 significant digits, that's 1100. I'll do a few examples here. Two more on this subject. I got it. Another example. I was driving by Chicopee, and the guy actually had a sign hanging. It looks like this. There's a beam holding it. There's a rope holding the sign up there. So the rope is pulling up there, and the sign says honey for sale. He was selling honey. even better sign. Since you guys leaving us soon, instead of honey for sale, and a sign that says, I love physics. That's a better sign. That's it, because I know you all love physics. The question is, we have to give you weight for that sign. Let's say the mass of this sign is 20 kilogram. The mass of this beam, 30 kilogram. Let's say this angle is 20-degree angle. And what I want to know, a couple of things. I want to know what the tension in the cable here. There's a string holding that. This piece here has to be held. Let's say there's a hole in it. In the middle of the hole there's a screw there going through, or a nut going through. So the beam is free to move, this beam, up and down. So there's a pivot point right here. Well, if there's a pivot point right there, there's probably a force pushing in this direction on it. And a force pushing, I have no idea if it's up or down. I really couldn't tell you. I'm going to say it's down. I have a feeling it's going to be down, but I might be wrong. I have no idea what these forces are. Let me call this force F in the X direction and F in the Y direction. It could be up, could be right, but I'm assuming if this attached to a nut there, a screw and a nut there, it's keeping it from going up or down. It wants to go, because if you just dangle any weight, this wants to go up. So it must be pushing down. If I don't have that beam, this probably will move down, straight down this way. So there's a force pushing in that direction. And the sign is not moving, just sitting there. So my free body diagram, here we go. Let me draw that nice and clean. I'll make this. We have the weight of the beam itself in the middle of it, uniform beam here. I never gave you the length of the beam. So let's say 1 meter long. So we have the weight of the beam, which is 30 times 9.8. $294. We have the weight of the sign. That little sign says, I love physics. The weight of that is mass times gravity, 20 times 9.8. We have the tension pulling up there. What's that noise there? Huh?
Sounds like they're drumming something.
Oh, maybe. First I thought it was my stomach, but. We have f of y, which I took a guess that says coming down. If the value is negative, that means I'm wrong. It's pointing upward. And I took a guess on f of x is pointing in this direction. And that's the pivot point, because it's attached to the nut right there and makes a move right there. What I'm going to do, take that force here and break it down to x and y component. That T, if I break it to x and y component, I will have Fy this way, Fx that way, $294 down, here we go, 196, If this is the pivot point, this is 0.5 meters. This is 1 meter here. Then I'm going to take this force and break it down to two components. One in this direction and one in this direction. The one in this direction is what? T sine 20. And the one this direction what? T cosine 20. And again, if the sign is not moving, just standing there, hanging there, we have static equilibrium. And if we have static equilibrium, we have three things. Sum of the forces in the x direction, the net force in the x direction is 0, which means if you take the forces pointing to the right, they should equal all the forces pointing to the left. What do we have pointing to the right? F of x. What do we have pointing to the left? T cosine 20. One equation, two unknown. Sum of the forces in the y direction, the net force is 0, which means the ones pointing up should equals the ones pointing down. Pointing upward, what do we have? T sine 20. Pointing down is what? 196 plus 294 plus Fy. Now I got two equations by how many unknowns? Three unknowns. I got Fx, T, and Fy. Can't solve it. The last equation. Sum of the torque or the net torque should be 0. Let's take this pivot point. Any force that goes through the pivot point has a 0 torque. So this has 0 torque, this one has a 0 torque, because the distance r is 0. So these two have no torque. So is this one, because if you extend that, that's going through the pivot point. The distance from the force, the perpendicular distance between the force and the pivot point is 0. So this, and this, all three of them have 0 torque. So the only one's going to make that beam spin is this, and that one. Let's begin with this one, the 294. And that's going to make it spin which way, clockwise or counterclockwise? That's a negative, right? 294 times 0.5. The 0.5 is half the distance because that's 1 meter long, the beam. This one, the 196, is going to make it spin which way, clockwise or counterclockwise? That's also a negative. The distance is 1. And the other one is this one, T sine, and that's a positive torque because it's pulling upwards, going to make it spin counterclockwise. That's a positive torque, and the distance is 1. And that's my third equation. Negative 147 minus 196 plus, what's sine 20? Sine of 20, 0.342 times t. So we take these two numbers, 196 plus 147, move them to the left side, they become positive. Can we get what the tension is? 343 divided by 0.342. 1,003. Once you know that, can you find f of x and f of y? F of x is going to be t, which is 1,003 cosine 20. $942. Can we get f of y from that equation? 1,003 sine 20 equals 196 plus 294 plus f of y. 196 plus 294, 490 plus fy equals 1,003 sine of 20, 343. Guess what? I was wrong. Look at f of y. It's going to be what? It's going to be a negative number. Negative 147 Newton. Which means I thought it's going to be pushing which way? Down. They're saying, oh, no. This force is going to be pushing which way? Upward. So f of y is going to be pointing actually upward instead of down. This is how you're sure. I'm not going to do any more problems with these. I'll hit the whole thing next week completely in full detail. But